Hey guys, welcome back to another episode of Robo Papers. Today we have four authors, the biggest one, the biggest podcast we've done, where we have so many authors from the same paper. So the paper is Sim and Real Co-Training, a simple recipe for vision-based robotic manipulation. Yeah, thanks for making it for the pod, guys. Maybe we can do a round robin, each of you go through and introduce yourself a little bit.
So, hi, I'm Sarush. I'm a PhD student at UT Austin, advised by Professor Yuka Zhu. So, I'm interested in training generalist robots by tapping into diverse data sources, and it's great to be on the podcast.
Hi, everyone. I'm Avi. I'm a fourth year undergrad at UT, also advised by Yuka, but I've spent a lot of time working with Sarush the past 2 years. And yeah, I guess my interests overlap a lot with Sarush's. I've been doing a lot of work with looking at data curation, how that allows robots to generalize better, looking at a lot of multitask settings. So yeah, thanks for having me on as well.
Everyone, I'm Jenny, same as Avi and Suresh, also supervised by Yuka. I'm a PhD student, and my research focus is on more like building simulations and leveraging simulation for real-world manipulation.
I'm Lawrence. I'm currently a fifth-year PhD student at UC Berkeley, advised by Professor Ken Goldberg. My research focuses on cross-embodiment learning and, in general, how to make policies more robust to different factors, different robots, different camera angles, different objects, generalization.
Okay, perfect. Maybe one of you can share screen, and then we can start with an overview of your paper.
Yeah, so this was a effort involving some people at UT, some people at NVIDIA, UC Berkeley, and NYU. And the premise of the project is that, well, we all want generalist robots, and to get there, we have to collect a lot of data. Like, I think we all agree that a lot of data is required. But doing this strictly in the real world is going to be quite expensive. And so we wanted to look at trying to harness other data sources, in particular simulation. So the paper title is Sim and Real Co-Training. And basically the idea is, instead of training solely on, data collected from real world robots, we actually additionally co-train with large scale simulation data. And so we actually have, an entire study dedicated to this setting, where we look at two distinct settings. One is with a single arm robot, but we also look at a humanoid robot. And so in these cases, we're interested in performing a wide range of tasks, and we want to show like a recipe for co-training that's broadly applicable across all of these settings.
Yeah, and just to add to that, so before this kind of co-training project came around, I work with Sarush on Robocasa, and a big part of that is a big focus we did in Robocasa was kind of creating a very highly diverse and high fidelity simulation environment, right? We made sure we did a lot of studying and making sure the object sizes and the fixture sizes in Robocasa were all realistic, true to the world, and we also did a high focus on diversity with generative textures, and kind of the natural next step in that was seeing how well our efforts to create high fidelity would lead to sim to real transfer. Yeah, that's kind of how it first got started.
Yeah, so Abi and I worked a lot on the Panda robot side of things, but then there's also this other component, which is using humanoid robots done at NVIDIA that Yu and Lawrence really led. So if you guys also want to chime in there.
Yeah, sure. Maybe I can take a first steps. Yeah. So actually, before this project, I was working on a project called Dexter Vision, which is about generating simulation manipulation data for humanoid robots, many robots like humanoid robots. Similar to Robocasa, after we got the whole bunch of, bimanual manipulation data, the next step is how do we really leverage this simulation data for real world manipulation? And we gradually converge on this numerical training and idea, because Serge and Abi has shown some sign of life in Robocasa project. We want to see if the same co-training recipe is it's applicable to both simple term as well as a more high degree freedom manipulators humanoid, and that's where we start this effort.
Yeah, perhaps you guys can talk us through this. You have this task aware like simulation, and then a task agnostic, a more general one. Maybe you can talk us through that setup, or maybe also to just the overall architecture, the whole pipeline.
Right. Okay, so the premise of the study is to combine real world data and simulation data and to co-train on it. And so for the real world task, you know, there's no sim to real gap that we have to worry about. But the downside of that is that the data is somewhat expensive to collect because, robots in the real world are expensive and they can break down, and data collection in the real world is also a laborious process. So we wanted to also tap into simulation data. Now, for simulation data, we looked at two distinct settings. The first setting is task agnostic simulation. So the idea here is sort of like, think about it as let's say there's a bunch of simulation data that already exists, maybe from other projects, other efforts, and you just want to use that simulation data out of the box. So you want to download that data and you want to directly co-train on it. And so first we wanted to see, like, in this most like simple case of just take whatever simulation data is like already out there. How well does that help? Now, additionally, we looked at a task-aware simulation. So the idea here is, let's say that we want to take some extra steps to better align the simulation with the real world. So we might take some existing simulation frameworks and we might do some tweaking on top of them to better align various factors between the simulation and the real world. And so we wanted to see, compare the relative strengths and weaknesses of these two types of simulation data, and to see ultimately, like, what is the kind of juice that we can extract in either of these settings.
Yeah, and I think we had a formal definition somewhere.
Yeah.
So one thing stands out to me about this. So you have all these pictures of the simulation, and I noticed that it doesn't look all that realistic. So could you talk a little bit more about that? Like, what did you need to do to get the simulation to work on that side? Like, were there any requirements?
So a lot of the simulations that we used are built on top of Robocasa. So Robocasa was this project that we worked on a couple years ago, and then we released last year. The focus is to simulate everyday activities in everyday environments. And Robocasa comes with a lot of great features right out of the box, a lot of object diversity, scene diversity, and customization, like to be able to build our own new tasks and to be able to tweak things in the simulation. So we use that as the kind of the starting point. And in terms of what Robocasa offers, there's a lot that it offers, but there's also a lot that we see is, what we call a sim to real gap between what Robocasa shows and what you see in the real world. So, one of the most apparent things is the visual gap. And so here we're actually showing, like, the images from our real world kitchens right up here versus the images that are rendered in Robocasa. And you can see that there's a clear visual gap, but we didn't really make any efforts to make the renderings like more realistic. We were actually trying to inject the least amount of like additional effort to align the simulation with the real world, and we noticed that it can help quite a bit.
Yeah, I don't want to derail everything, of course, but I think it's something interesting to note, right? Because it seems so then in your mind, from your paper, you would say that like visual realism, like getting beautiful shadows and nice textures and all this is less important than the things you mentioned earlier, like being able to portray a wide range of objects and tasks that you specified. Is that true?
Yeah, so I think,
Among other things, I guess.
we have to put a caveat around that, which is that it's like a lot of the developments that we see here is also tied to the model. So it really depends on what kind of image resolutions these models are operating under. And so the kind of models that we trained on, like, the image sizes are relatively small. They're about 128 by 128 pixels. So when you take, like, really beautiful images with like all the realistic shadows and things like that, a lot of that might already be lost in translation when you're training models on like relatively smaller images. Most of the like training these days is not like training on like high definition images anyways. So it is important to note that our findings are somewhat linked to the current status quo in terms of model training as well.
And just to add to that a little bit, like, and Zhenyu can also comment on this a little more. I think like to some degree the model is able to like kind of differentiate it provides a little bit of different actions between like when you roll it out in sim and when you roll it out in the real world, and that's something we kind of can tell, I suppose.
Yeah, that's definitely true. So yeah, I think so we definitely we find that co-training works like surprisingly works pretty well like across different settings, different tasks. But we do want to understand like why it works, for what reason, just with this like crappy simulation images it somehow starts to work. So one thing we were like previously assuming is like, okay, somehow during the training process the simulation and the real world kind of like merge together in the state space. But it turns out that's not the case. We do some facial visualization, and it's also revealed in another concurrent paper on like simulation co-training. Basically, we both find that the policy actually can discern like simulation observations from the real world observations, but somehow it's still like adding the simulation data still helps with the real world policy performance, which is like quite interesting. I think that's also relevant to the fact why you see like these simulation images are not super realistic, because it doesn't need to really merge or fuse the simulation and the real world in the training process to make it really help. It doesn't. That's not like the core driving force behind the reason that why similar co-training works. I think that's kind of like the case.
Yeah, that's actually super interesting, because that would be my first guess, is that because they're so different, it would be able to learn like a separate pathway for each one if it had the capacity to do so. So the fact that it both does that and still gets some benefit of learning both of them is really interesting.
Yeah, but like one thing we did find is like in our initial experiment, we do have like one case where like it's the same task, but the behavior is a little bit different. It's like when you're placing down the object, if you're placing down horizontally or you're placing down like vertically. We found like if you in simulation and the real world, if these like behavior modes are very different, then co-training does not help with the real world policy. So we assume that our assumption is that you have to have the similar behavior mode, and that's like one of the more interesting factors that is driving these things to work.
Yeah, and I mean, this is not to say that like the visual differences are not important, because we had another experiment where we showed that camera alignment is relatively important. So again, we don't have to like precisely align the cameras between the simulation and the real world, but we did a controlled study where we tried to create a bigger source of camera divergence between simulation and real world, and we saw that the performance was dropping. And so, but just given like the whole picture of what we did, I think we found that motion, like the motions and the actions and the behavior distribution, it's more important that those are aligned rather than strictly the visual features.
And just to add to that, we do have a study to see if making the simulation rendering images more realistic can help. And we do see that in the low data regime, when there's very little real data, and we mainly rely on simulation to help, then making simulation more realistic can help about like 10% success rate improvement. But when it's in the higher data regime, they actually learn both pretty well. And then this making it more realistic has very minor benefits.
Is that holding the real data constant, or is that so like with lots of sim data? With lots of sim data, you lose the need for it to be really realistic, or is it that with lots of real data, you lose the need for the sim to be realistic?
With more real data.
Gotcha. Yeah, makes sense. Of course. Okay, interesting.
Yeah, maybe you guys can share a little bit about like those three. Basically, you have three sources of data, right? In your study here, you have real data, and then you have the task aware, and then you have the task agnostic one. Could you talk about each of these? Like, how do you collect those data? How do you set it up? And I know you have some study of like a different like proportion, but maybe just how those data is being collected. If you guys can talk us through a little bit.
Yeah. So I guess starting with like the task agnostic prior simulation, like that that's just like a data set I just downloaded from Robocasa, like the Robocasa website, right? Like as far as like who collected it, like data collection details, like it's all like it can be anything. And the only thing I did on top of like just downloading the data set is like rendering it in a similar camera angle as to the real world. But as far as like digital cousin, that kind of the idea of digital cousin like came from like a previous paper, and that kind of comes about after we know the task. So we create a digital cousin to the real world task, and that requires like some like small amount, maybe a day's worth of effort just to create the task and then collect like maybe 50 demos, and then we use like Dex Mimic Gen to get maybe like 100x of the original 50 to 100 demos.
So just to double tap on that. So when you say, let's say 50 demos, this is like a human doing things in simulation that is supposed to be a close digital twin to the real world data set, the real world task.
Yeah,
And then at the
exactly.
same time, you also have a real world task with a real world robot, which also is teleoperated. So that then forms your what you call the real world data, right?
I guess the digital cousin would be separate from the real world data, but that's would be like the task
Yeah.
aware data.
So this flow chart sort of
Mhm.
shows what we're trying to do. So let's say we have like a particular real world task in the kitchen. We're trying to rearrange some objects. So one source of data is just like doing teleoperation in the real world. Common approach that a lot of people do. So what we do here is we just collect like, on the order of about 50 demonstrations per task using teleoperation. So that's the source of real world data, but it's, relatively small in nature. But then for the digital cousins, so what we do is we essentially like create a like very similar task in simulation, but it's not, the details are not exactly aligned. So that's why we call it a digital cousin rather than a digital twin. And so this term digital cousin has been sort of introduced in prior work, and we're adopting that here as well. So once we create the digital cousin, then we'll do the same thing where we'll collect like a small amount of demonstrations with teleoperation. But then because we're in simulation, we can leverage these powerful, frameworks like Dex Mimic Gen that allow us to significantly multiply the data almost for free. So rather than going through the effort of collecting thousands of demonstrations ourselves in simulation, we just need a small number of seed demonstrations that we collect through teleoperation. And then Dex Mimic Gen will automatically create, order of 100 times or more data in simulation. And of course, we also look at the task agnostic prior data, which we just download from the internet. And these are basically the three sources of data. And then, we can choose different ways of sampling from them. Like we can put different weights on these different sources of data. We can choose to use only digital cousin data or only task agnostic prior data, or even both of them at the same time. And so our study actually goes into, like different data set compositions and different weighting schemes. One thing in particular that we find is that the sampling ratio is important. So if we have one quantity of real world data and another quantity of sim data, if we just like kind of concatenate these blindly and just like sample from them without weighting the data, we actually don't get the best performance. So it's important to like kind of set the right ratio for sampling these different kinds of data because they occur in vastly different quantities.
In fact, you have this particular chart in your paper that I think maybe capture what you just said really well, where I think you have this split, and you're showing the split, like how much simulation data as you evolve. Let's say I'm trying to see, which chart I'm talking about. Oh yeah, data composition. Yeah, I think. Yeah, you have real plus DC, and then real plus prior, and then real plus DC plus prior.
Yeah. So these are the some of the experiments that we had, and we basically look at what happens if we train on different combinations of these individual data sets. If we train on real only, if we then but we always want to co-train with real data because there's always going to be a gap between the simulation and the real world. So everything is like on top of what happens if we add simulation on top. So, but there's different kinds of simulation data. There's digital cousin data, there's task agnostic prior data. And so we want to see like all the different combinations and see how much they help. And yeah, if Jenyu, Lawrence, you want to also chime in.
I mean, I'd be really curious to actually, how do you think it would do with just the simulation data, especially on this closed door task here, where it goes from 10% to 100? That seems like something where it could actually might just work simmed real, right? Or do you think no, not really?
Okay, so I'll also let the other people chime in on this. Personally, I think it has a good chance of working because the way I view simulation is I don't view it as a completely separate entity from real world data. If your simulation is relatively diverse and relatively realistic, then you can sort of view simulation as another real world environment. And what we saw like with the recent Pi 05 release this week is that they essentially collected data in a bunch of like training environments and then they deployed them zero shot in testing homes. And so you can sort of think of our simulation data as data from the training environments, and then the real world environment would be the testing homes. This depends on the complexity of the task. It depends on how much of a gap is there between the data that you train on and then the test settings. But I think in the easier cases, you might actually just see some zero shot sim to real transfer.
Yeah, that's why I would think about the closed door one in particular, right? Like, so you have like a pouring task where it goes like 65 to 90. I totally believe that it needs the real data there, right? Because like most of the performance seems to be coming from the real data, and then but it doesn't generalize enough. Like the other one, like closing a door is maybe less precise. I can imagine, right? I don't know. It's interesting.
Could you guys comment about like just the relative sizing between these three? Like when you say real, like especially the last one, real plus DC plus prior.
Yeah, so for real data, I think for these two sets of difference, they have like slightly different numbers. I can talk more on the humanoid side. For the humanoid, real only have like 20 real world trajectories. DC has like 1K trajectory per task. The prior, they're like 1K per task, and there are 10 tasks, so it's like 10K simulation data. So real plus DC plus prior is like 11K plus 20. That's size in terms of humanoid. And I guess for the number of like panda, maybe Abby can elaborate a bit.
Yeah, so we start with the real, it's like 50 demos, and then the digital cousin. So we collect around like 100 like human demos, and then we upscale it to 10K with the mimic gen. And then the prior is around like 60K across 20 tasks.
Yeah, so actually like the real is less at most a fraction, like 1% of the whole thing, if you just look at it this way. And then with the task aware one, you collect some, and then you also use mimic gen to drastically increase that. So it feels like the DC and the prior is, I guess it really depends on how much prior you have. But the DC in theory, like, is there any reason why you do it, from 100 to 60K, the mimic gen? Is there a reason why you stop there? Like, why don't you do more?
Yeah, so for humanoid side, basically what we found is like we're doing like only 1K trajectory for DC. And we find like in the simulation performance, when you get to like 1K, it's almost saturated. So like increasing more simulation data does not help in the simulation evaluation significantly. So we just stop there. Yeah.
Yeah, so I think it's very much task dependent and like, what is the space that you're operating in? Are you operating with like hundreds of objects and like hundreds of scenes? Or are you operating in like a very narrow domain? And so that's gonna, dictate different amounts of data ultimately you need to solve these tasks. And the thing I want to highlight here is that this is just the first step. So we just try to use like the existing simulation frameworks that we have. We could have like increased task diversity, we could have increased scene diversity, we could have increased the quantity of data, but we just wanted to see the first signs of life. And obviously the next steps would be, what happens if you try to like 10x 100x the amount of simulation data, also with the real world data as well. Like what happens if we instead of having 50 demonstrations for the real world, what happens if we have like 500 or 5,000? And what we had some experiments that we'll get into that as well later. But this is like a really promising first sign. And one of the things that we're working on right now is just to increase the scope of diversity in our simulation. And so, once you have like 10 times the number of tasks, 10 times the number of scenes, 10 times the number of objects to operate with, then like naturally that's going to necessitate like generating also more data. So then we'll also generate like much more simulation data. So these are some ongoing works that we're working on.
Makes a lot of sense. So one thing that I actually thought was super interesting was this real sim mixture parameter alpha. Could you talk a little, like, what does that have to do with any of this in this case?
Yeah. So Jenny, if you want to go through it.
Okay, sure. Yeah. Yeah. So this is like it's basically how we collate the simulation and the real world data. Basically, in the training, you want to sample some data from the simulation and want sample some data from the real world. Our definition of alpha here is like basically like in a batch, how many percent of this batch is sampled from the I think it's sampled from the simulation data. Interesting thing is like in our like initial experiments, when we start doing this project, we were trying naturally we wanna do not, because like we have way more simulation data than the real world data, so we don't want to like oversampling simulation data, basically to just do natural sampling, but a ton of like simulation data, but with a very little fraction of real world data. And so we do this like 50-50%, which is like it's kind of like you upsample the real data intentionally. So to make sure you have like a 50% chance of meeting real data like during training. And that one works, but not very well. And later, I think it's one day I suddenly it comes to my mind, what if I just use natural combination? What if I just, combine them together? Like 1,000 simulation data, 20 real data, put them together. We don't do any upsampling. It turns out to be working like pretty good. And it's much better than just like 50-50%. And then we just use that ratio in the future experiment. But the reason we didn't keep using this like a natural combination in the old experiment is because if you're co-training with like a sim plus prior, that means like have like 100 more simulation data than real data. You barely see any simulation data. That's why in the ratio of like a 99.9, which is like I think it's like 1,000 versus 1. That in that case, like the simulation is not helping real at all. That's like it's an interesting like finding that it's not like natural like do this balancing is not actually a great idea. You really need to tune this ratio to make sure sim helps real.
Interesting. So based on what you're finding in each batch, basically the sweet spot could be like 1 to 10%
90%.
real, and then
Yeah.
90% each simulation. So
Yeah.
in
Yeah.
theory, your simulation data could be 1 million x what you have in real, but maybe what you suggest here is you would still want to sample roughly like 1 to 10 or 1 to 100 at maximum, something like that.
Yeah. That's correct.
Interesting. How about this other table on the left here? Could you comment about this the difference between?
Sorry. Yeah. Okay. Sorry. I keep like interrupting you, but yeah. So I think the left figure is actually a more encouraging figure because, as we have discussed previously, we're using like a low number of real world data, like 20 or 50. So like we want to see like if you keep increasing the real world data, would the like benefit from the simulation data diminish when you like keep growing this real world data, like, and to what extent it will diminish? So we actually try this on this specific like it's actual experiment setting where we have like it's like 4 different combinations of objects, and we call like a multitask PNP. So like it's pick object and place object from different containers, and we have like 4 combinations. So in this experiment, we try to increase the number of real demo from like 40 to 400. We do find that there is no like a diminishing effect in this experiment setup. And with more simulation data, you can still see like significant boost from the with more real data, you can still see a significant boost from the simulation data. And yeah, so we stop at 400 because like collecting more data will take too much time. So we just stop there.
That's a lot.
Yeah.
Yeah. One really interesting thing about this was that so your 400 demonstrations though, so you're collecting your real data of one environment, right? So like so that would mean that is then are the results that you're seeing then because, in your opinion, because a lot of the ability to generalize is coming from like the really wide range of simulation environments that it's seeing. So most of the diversity comes from the simulation if I'm understanding what happened right. Is that correct?
Yeah, that's a very good point. That's actually pretty correct because in here we as I mentioned we're doing this multitask PMP, so there are some combinatorial generalization like cases, and in simulation we literally just like randomize swapping the objects and very diverse background objects, stuff like that. It greatly increase the policies like robustness to this novel cases. I think that's one important reason why sim helps really revealed from this experiment.
I mean, just to add to that like point on diversity, like on the Panda side, we also did an experiment where we restricted the task to one kitchen environment, and we did see like a non-trivial drop off in performance.
Yeah, so basically, like, we did various ablations, and what we saw in general was that, like, increasing the scope of diversity in simulation, it generally helps. Like, whether that's over objects or whether that's over the training environments, over tasks, over the quantity of data. So just basically scaling all of these things up, like, they all play a role, perhaps to different degrees, but we see as we start to train these robots on like bigger and bigger models, that also gives us the opportunity to also like train on more and more diverse and larger data sets, in this case simulation.
Yeah, I'm curious. Where do you think eventually this will land, right? I mean, if you project this further, so it sounds like you guys are already thinking about like scaling this up, just having a lot more simulation and maybe also a bit more real world data. The question, I think the thing about simulation I never can quite wrap my head around is that in theory, the search space or the exploration space is nearly infinite. So there are just so much things that you can simulate, right? Different lighting, even the tablecloth, it could be just maybe infinite pieces of it. So I think beyond a certain point, things will saturate, but I think it's hard to know, maybe perhaps like before the fact, like which dimension would you saturate first. And then because you might run the risk of like just like wasting, I don't know, like committing GPU compute to diversity in the simulation dimensions that actually doesn't move the needle, and you kind of only know it after the fact. Or do you guys think that actually just trying everything it's fine, because like compute is still a lot cheaper than real world data? Like, how do you guys think about that?
Well, I guess the first thing I want to say is that it's not necessarily about simulation versus real world. So
Mhm.
I think that, and I think I speak for the co-authors here as well, we're not trying to diminish the role of real world data. So real world data is important, and there's going to be a lot of efforts to scale that up and to do that efficiently and effectively. Something that's really been promising that many different research groups are sort of converging towards is that co-training is a really effective strategy. When we saw from like the work of RT2, where they co-trained on web data and they saw it transfer from those internet scale data settings for robotics applications. This is you can sort of view this work in the same line, which is we're trying to transfer capabilities from one domain to another, because ultimately we can't solve the entire problem by just solely collecting data like in the real world. We want to be able to tap into internet data sets. We want to be able to tap into simulation, and we want these things to coexist and to help each other. And so this is part of like a more grand vision to unify training across all of these data sources. And I think many of the recent papers on training these generalist robots have are sort of recommending the same thing, that it's about combining capabilities, combining like high level reasoning, planning, low level perception, like bounding box detection, and then robotics data sets, and then combining robot data sets from like in the wild scenes and also like static lab scenes. And the contribution that we're trying to make here is that we also want to incorporate simulation data. And so simulation data can be an important part of the solution. And so with that perspective in mind, the next steps are really to scale this up and to do it, in a way that, basically like leverages all the benefits of simulations. The benefit of simulation is that you have access to ground truth state information. You can use that to generate lots of data autonomously, and that's something that we've shown in MimicGen. And you can also, like annotate data because you have access to, again, the ground truth information from the simulation. So a lot of this can just come for free without necessarily expending like additional human effort. And so we really want to like tap into that, and we also want to look into what's happening in the generative AI space and to try to incorporate a lot of those tools into simulation. So rather than kind of like manually building assets, we want to use generative AI tools to generate assets from objects to entire scenes to even tasks. And so the more of this we can automate, like using these tools by integrating like generative AI tools into simulation, um, I think the bigger of an impact that we can make.
There's also one aspect that we really haven't talked a lot about here is in what way the simulation helps the most currently. Currently, we see the numbers improve, but behind the scene, there's different ways how we measure these numbers. For example, if we only care about one particular task, about only the training objects, or we care about generalizing to different objects but in the same environment, or we care about different tasks or different behaviors. In our study, we see two major areas where we see benefits. One is generalization to like unseen objects, and the other is unseen positions. So about the objects part, that is more about robustness, where when we swap out a Coke can with a Sprite can or with some other bottles, the policy of grasping it should be still robust and should be robust to lighting changes, etc. A clear area where simulation can offer a lot of help because of the render capabilities and the background that we can do randomization simulation. And on the point of new novel positions, we see that simulation can give us robustness in terms of interpolation. When we have some sparse data points in real and the simulation kind of more densely sample the locations, we do see that the behavior becomes more robust and more smoother. Besides these 2 points, we have not yet seen a lot of behavioral extrapolation or new behaviors coming from simulation directly transferred to real. And I think that is something that is remain an open area of research. And beyond that, on the topic of single task versus multitask, I think in single task, we do see that simulation also helps a lot, but the kind of like performance saturates. There's an upper bound depending on the task difficulty. But where simulation can shine the most is where there's a multitask situation where it's really impractical to like collect all the combinations in real data, but then it's possible in simulation. And having that and maybe combining with semantic capabilities with the VLM is the best combination.
So I think this is like one thing we want to understand, like in what case the simulation helps the most, because as Lawrence mentioned, you want to understand like in what test scenario it works. We want to like test like in domain distribution, like the same object is training, the same setup as training, as well as like the other domain deal with like novel objects or novel setups. And our experiments, so if you look at the table 2, which is like highlight right now, is like where we mainly test like this thing specifically. First, we have this unseen object. So basically, if you train only with real world with real world data, the both like Panda and GLI struggles with like unseen object, but once you co-train with simulation data, they become more robust and gives higher success rate. And for unseen position, we're doing something quite like specifically, because so initially what we wanted is something like you can see if you can extrapolate. For example, you initialize the object in a small small box, and you want to see if, and in simulation you generate data in the whole workspace, and you want to see if the simulation data can help it extrapolate its initialization range. And unfortunately, that's a good hope, but it didn't work out. So what we did instead is okay, extrapolation does not work. How about interpolation? So basically, we have as I think I'll be showing later on. It's we have a workspace. When we're collecting the real data, we specifically collect the real data where the object is put on the boundaries of the workspace. And during testing, we test if with the object inside in the middle of the workspace. Definitely in simulation, we still generate data all around the workspace. And in this case, we found it's particularly pretty helpful. So I think that's what we're saying. We kind of show how simulation, what new capability the simulation data offers with the real world policy.
Yeah, that's
And
all
sorry,
really
can I ask, are they
interesting.
the same task that between the panda arms and the humanoid? Are they taking out the same tasks? I'm just curious that the success rate was quite different between the two.
It's different tasks. It's different tests. We have we have two teams, Avi, Susha, Hannah, and Lawrence and I was working on humanoid. So we have take a quite different task.
Oh, got it. I see. Okay, cool.
Yeah, I'm curious if part of what simulation data is doing here, especially since you're mixing it into the training with that alpha parameter, is acting as a regularization. Do you think it would be better at sim to sim transfer, like an unseen sim or an unseen robot, with them because of the ratios that you're using?
That's a very good point. So that's actually one thing I was doing during this project, because real world evaluation is just too painful, especially with the humanoid robots. So I was thinking oh, okay, how about let's do sim to sim. And interestingly, we find that sim to sim does not equals to sim to real. So what I tried is, you see we have this DC data and prior data, and in the real world we show that co-training the real world with prior data also helps. So what in sim to sim, what I did is okay, I co-training DC data with prior data, so that I still take 20 demos from the DC data and training with 1,000 prior data and 10,000 prior data, and just use the same alpha ratio and same thing. And it turns out it's not really helpful. Somehow sim to sim is not super helpful, but in sim to real is helpful. I guess that kind of pretty interesting, because we would assume or it's pretty in some way insightful, because it's the gap between two simulation environments or two simulators. The direction between this this difference vector might be different from the vector between a difference vector between the simulation and the real world. So yeah, I think it's the interesting question.
Yeah, that's really interesting. Okay.
So I guess maybe I think maybe you guys can talk about some limitations that you guys mentioned in the paper, or maybe also that we set up for potential future work that extends from this paper.
Yeah, I can start with one limitation, and then the others can comment further. So so I think the tasks that we studied, they are really relatively more simple in nature. So they're pick and place tasks. There are some other tasks as well, like closing doors and pouring. But we want to be able to also show that the simulation data can help for dexterous tasks and longer horizon tasks. So that's not something that we looked into. It'd be interesting to see what happens. And I'd say a sort of related limitation is that the scope of diversity for what our simulators currently offer is still somewhat limited in nature. Like the sheer number of tasks and the amount of data across those tasks, that's still there's a lot of room for growth. And so there's some separate efforts that we're working on towards significantly expanding the scope of tasks and environments and data as well in simulation. And I'm really interested to sort of repeat the experiments that we did in this paper once we have the next generation of simulation that we're working on, to see what sort of insights stick, and then what sort of new findings that we have.
What are the biggest changes you're trying to make to the simulation?
So we're not really trying to change the ethos of what we're doing. We're just trying to x every axis. So we're trying to have a significantly higher number of scenes. We're trying to have a significantly higher number of like appliances, like in terms of these kitchen environments.
So more diversity of objects and motions and lighting and all
Yeah.
that kind of stuff. Okay.
And,
Yeah.
two other big factors are the tasks, so the number of tasks, and also the data for those tasks. So I guess those two come hand in hand.
Yeah, and just adding on to that, one thing, at least on the Panda side, that we would like to improve is like we kind of want like the generalization. Like right now, like it gets like 50% for novel objects and like 28% for novel poses. Ideally, like we would want those to get higher and do similar to like our novel setting and even extrapolate, as Lawrence mentioned. And yeah, I think just another similarly, we just think we could get that just by scaling the diversity by like 100x.
So that's definitely like I think a necessary component. Perhaps that might not be a sufficient component because it also matters like how well the data is like curated. So one of the things that we've noticed is that compared to the human demonstrations, like the mimic generated demonstrations, we see a range of data quality. So although all of the generated demonstrations technically perform the tasks, some of them are more pleasing to the human eye than others. Some of them have like jerkiness and things like that. And so this is like I'd say like just, good old fashioned engineering that we need to do to ensure that not only are we like generating like lots and lots of diverse data, but also ensuring that the data that we're generating is also like extremely high quality. I think we need to focus on both of those.
So does that mean any work needs to be done so some work needs to be done in just improving mimic gen to get those trajectories to work better or provide better reference data?
Yeah, so Mimikgen, like it's a really powerful tool, but as you try to apply Mimikgen to these more complex settings, potentially where you involve mobile manipulation, that's a place where you need to pay attention to the details. And so those are some things that we're working on, and I think like there's a lot of areas for like low hanging fruit where we can, you know, upon the quality. Some things will take more time and effort. I think it's like really promising to continue pushing on that.
I can give some my own takes. I think, yeah, definitely first is about the task, I think Suresh mentioned. We were actually trying on this direction a bit. Like if you look at the appendix, we do have a task where we have like we call it bimanual pick and place, basically like take a cue from the left to right and from the middle to the left, from the left to the middle and from middle to the right. So we do have some try and see some sign of life, and I think it's actually pretty interesting because with this like increased degree of freedom, you might see different behaviors in simulation training. So I guess we definitely want to expand the scope of this experiment to make sure it works. And another thing I think that is pretty important is to understand why it works. We have discussed in a previous conversation, like it's not merging the same and real representation, it's not merging the same and real features, it's actually distinguishing them. Like then why does it work? I'm saying like understanding why it work can help us better, build the future build the future's co-training paradigms. Like what type of data should we include? Should we include more like in terms of like diversity in behaviors, or should we include in terms of more diversity in terms of like scene setup? I think that's another key question we were not able to answer in this paper.
Yeah, another area that is future work is how we can, beyond physical simulation, can we use generative augmentations or generative AI to synthesize new demonstrations from both real and simulation data that could give us, for example, changes in textures, in behaviors, in objects, in tasks that allow us to relieve some of the effort of creating new assets, creating new demonstrations, and getting us more diverse behaviors. And whether currently we have some sign of life, for example, improving like the realistic of the visual renderings, but we haven't been able to really take more advantage of generating novel synthetic trajectories using entirely generative models, and that is something that remain more work.
Yeah, that last point's like super important. I think like as we go into the future, we are going to rely more and more on learned models. So a lot of building simulation these days is like just manual effort in terms of like asset curation and like defining the logic for, like how mimic gen works. There's not actually there's no learning going on in the way mimic gen works. It's a purely analytical system. But I think we're going to go to a future where everything you'll see will be generated. So all the pixels will be generated, all the action labels will be generated, and it's going to be a data engine that's like essentially like a neural simulator, and it's going to give us like a huge like source of supervision to additionally train our models, and that source of supervision effectively, like aside from the cost of generating that data, it will be for free, and it's going to allow us to generate like infinite combinations of various settings like motions, behaviors, tasks, objects, scenes, layouts. But these things will require like no manual engineering to actually like engineer these features into the simulator, because this is all coming from one learned model. And the reason why I think that that's going to work is because we're seeing like so much progress now with video models, and so they're able to generate like this like physically plausible situations. And so I think maybe taking some data from like robotic settings and co-training with like these video data sets will then allow us to use these video models for robotics applications directly.
Yeah, I have a follow-up question to that. So could you give us a sense of just the size of compute at this scale that you guys are using?
Yeah, so I'd say that, well, first of all, it depends on like the type of simulator you're using, and the simulator we use here is like ultimately built on top of Mujoko. So in Mujoko, actually much of the compute is CPU. The physics is happening with CPU, not with GPU, but the rendering is happening with GPUs. But like you could use different simulation platforms, and I'd say the amount of compute that we need, it can be done at a university scale. In fact, the data that we generated for Robocasa initially, the roughly 60,000 demonstrations that you see here, they were not generated on these like massive clusters, They were generated here at UT Austin with the academic compute resources rather than, hundreds, like 10,000, GPUs. And we were able to do that in the span of like a few days to a week. So of course, when you want to scale this up now, if you're trying to generate, like millions of demonstrations, then of course it's beneficial to have more compute resources. But compared to the cost of like actually collecting these demonstrations in the real world, it's significantly cheaper.
Yeah, that is one of the nice qualities of SimToReal, is that it is more. It's a more of a level playing field. It feels like a lot of the time.
Yeah. I do have a maybe somewhat philosophical question to ask you guys about simulation in general. I mean, humans or like animals in general, like I think we are far more data efficient, let's say, in how we like learn things, right? So I understand like simulation, we get basically speed up time in a way, and so that we can experience like maybe a billion lifetime instead of just one lifetime. But then at the same time, I look at let's say a tiny mosquitoes within like barely experiencing the world is starting to fly around, and when I try to like kill that damn mosquitoes, it will always fly away. So it's got damn good physical intelligence and very very low like power consumption, and it's barely seen any like training sample. So what's missing? Do you guys have some hunch on it? Or
I'm also happy to respond to this if you guys but you guys should try first.
Chris, yeah, anyone.
I mean, I think that the thing to remember is that mosquito doesn't have just its lifetime. That's a like neural network that's designed to be that's been designed by 4 billion years of evolution, right? Like it's got quite a lot of data behind it. That's my opinion. So I think a lot of what we're doing, like our neural network architecture in our brains it's got lots of specialized components, is very structured. It's not a neural network that we're learning from scratch in the same way.
Yeah, and even like a lot of the advancements that we've seen in LLMs, it comes from, this like pre-training, post-training paradigm where in the pre-training regime, you're actually training on like massive, massive amounts of like data in an unsupervised fashion or semi-supervised fashion. And that pre-training itself makes it so that you can solve, or fine-tune for downstream tasks in a very data efficient way. And so you can sort of view what we're doing here with the simulation as like the pre-training data engine. At least that's my personal philosophy, is that, I'm less interested in making these simulations like exactly match up with the real world. What I want them to do is to provide this bootstrapping effect where we just create massive amounts of data. And that data is essentially like what feels like pre-training. And then for post-training, we're interested in some specific downstream applications in the real world. So we'll collect, like a relatively modest amount of data, and we're able to take this model that has seen all kinds of different situations in the past, partly because of simulation, and that we can efficiently fine tune it to do, highly dexterous tasks in the real world.
Yeah, that's a great answer. Okay, cool. So yeah, we're trying to like bootstrap like millions of evolution into like maybe a data center or world of GPU, I guess. Okay, cool. Any like final thoughts from you guys about the paper? Like Zhenyu and Lawrence, any final things you guys want to chime in?
One thing is that we study a lot about code training in this paper. We didn't really compare with pre-training fine-tuning paradigms. Adam Wei from MIT, in his code training paper concurrent to us, they also studied pre-training, post-training, and the results kind of pretty interesting. They didn't find a lot of benefit, like after code training or just pre-training on sim and fine-tuning on real, like compared to code training sim and real. They found that actually code training is the best way, potentially because of overfitting when there's on the low data regime in the real data. And I think that's kind of interesting in the sense that when we think of pre-training and post-training, it's something that we want prior knowledge on, but if it's some task that we actually interested in, then having too little real data and just rely on pre-training on sim and post-training on real, or just even co-training in the pre-training stage may not be the best strategy. So there's some like training paradigms that remain to be studied more carefully alongside data.
Yeah, got it. That's actually a quick segue to our usual last question. Thanks for the shout out to that paper. We usually ask like, are there any like cool papers like that completely blew your minds recently that you want to give a shout out to? If you guys want to highlight some, our viewers can also like go and read up on those.
Yeah, I think definitely like one paper is like the paper keep mentioning the concurrent work from MIT, the Adam Wei's paper. Like that paper was more like in-depth analysis of like one specific task of the pushing T and do a lot of in-depth analysis on how it works, why it works, and they have some successful sim to sim like a result. I think they did some tuning for the simulator. I think that's also a very good paper, like doing more in depth where we are focusing on the breast, like try to see if it works generally in different cases. Yeah, I think that's definitely one of the paper that is very interesting.
Yeah, I actually want to give a big shout out to the Pi 05 paper, because I think these two papers are sort of saying the same thing, that you want to try to harness whatever data that you can get, and that the data will come in different forms. It can be data from simulation in the real world, and then how you obtain that data. Like in the real world, it could be from a lab setting, it could be from like directly the deployment environments. It could be web data. It could be high level like annotations of your existing data. And so what you want to do is ultimately you want a system that can do everything. So in order to have like, low level manipulation capabilities, in order to have high level planning capabilities, in order to have like robust instruction following, things like that, you are going to have to leverage different kinds of data coming from different places. And so this co-training paradigm is really taking off. And it's not just in robotics, you also see it in training BLMs. And so I'm really interested to, continue looking into that specifically. And maybe there should be like a more rigorous study of the science of co-training in general. We see that there's transfer when you try to combine different kinds of data sets, but the way that we're doing it is quite simple. We're just literally combining data sets together. we don't really understand like why. And this is again to echo what Zhengyu was saying. We don't really understand why it helps. And so if we try to dig into that science a little bit further, I think that can like inform us in how we try to better bridge the gap that might exist between these different sources of data.
Excellent. Yeah, I think that's a good way to end the episode. Yeah, thank you so much again for making the time. I think it's a really cool paper, and we should definitely maybe like talk to the the authors of the other paper as well, like get them on and share about what they did over at MIT. But yeah, I mean,
thank you guys.
thanks. Yeah, yep.
A lot of fun.
Looking forward to your next one. Cool.
Thank you
Yep.
for having.
Yep. Okay, cool.
All
All right, Chris. What have you learned?
Yeah, I thought that was it's a really interesting look at how to use simulation and real data. A lot of discussion about like what makes it possible to scale and to leverage simulation data to do better in the real world. Yeah, I really like learning about like the mixing and how different part types of sim data are valuable and what the challenges are, what makes it useful, all that kind of stuff. What about you?
Yeah, I think that like this general concept of just co-training, so regardless of whether the data is collected in the real world or from simulation, I think they all have their part. It seems to me that clearly teleoperated data have their own constraints, hard to scale. Simulation sounds easy to scale, but there's also like a lot of corner edge cases. So I think you need both basically, and it makes sense to figure out a training paradigm that involve both, which they've done in this paper.
Yeah, it was really interesting that it was valuable to use such different simulation data from the real world, and also that that it was able to tell the difference between the two. That like the camera angles mattered so much, but the other things is good to randomize. There's lots of cool details. That's a lot to think about. Cool stuff.
Yeah. So we should get more, I think, teams that do this kind of stuff on the pod. Yeah,
definitely.
Yeah.
Got a few lined up things to
yeah. Let's
Cool.
get those on. All right, cool.
Yeah, awesome.
All right, we'll chat soon. Okay.
Yeah, chat again. See ya.